Bismillah ar-Rahman ar-Rahim. Welcome to the next part or second part of lecture 29. We continue the Verilog introduction number 2. Okay, this lecture is about Verilog introduction. And last time, or on the previous part, we stopped at explaining, or we finished explaining actually, if statement. The most important thing to remember here is that these conditional statements, if and case, they cannot exist outside. Let me just drag this. They cannot exist outside of an always block. Okay, they have to be inside an always block. If you place it outside, if you place the if statement without the always block, okay, the compiler will complain to you. Okay, and the main point here is that this always block executes sequentially. Okay, and it will execute whenever one of its sensitivity input or list, whenever one of its variables in the sensitivity list is changed. Okay, it changes from 0 to 1 or 1 to 0. So this is an ALU. Okay, and then last time we derived the function table for it, and we see that whenever either the selection line changes or one of the input changes, C will change. Okay, so we need to re-execute or recompute C each time one of these three variables change. Okay, so this is what it means. So always at any change in S or A or B, execute this block. Okay, this is what it means basically. Okay, the syntax for the if statement is exactly similar to the programming language. So if you want to have more than one statement here, okay, you can surround it by a begin and end. Okay, but here it's just a single statement after the if statement. So when this is true, this is going to be executed. Else, if this is true, then this is going to be executed. Notice that S here is, if you notice that S is a 2-bit input variable, okay, which is the function selector of the ALU. Okay, so we compare it to 2 bits here. Okay, you have to compare it to 2 bits. So this is about the if statement. Now we would like to implement the same example using the same ALU using a case statement instead. Okay, and even case is similar to what you learned in C or Java. Okay, so you have an always block. It has to be inside an always block, like just like the if statement. Okay, then you have case S. Okay, and without any colon or something here, just case S. Okay, and then you have the cases here, and each case has a colon after it. Okay, and then you have the default case. Okay, so the default case corresponds to final else here. Okay, so when S is 0, 0, C will be A plus B, and when it is 0, 1, C will be A minus B, and when it is 1, 0, C will be A ANDed with B, and when it is otherwise anything else, it is going to be the OR of A and B, bitwise OR. Okay, and this one is bitwise AND as well. Okay, so this is about the case statement. So and this is the generic expression or generic syntax for the case statement. You have if your case, if one of the cases contains more than one statement, then you surround it by a begin and end. Okay, so for example, if case choice 1 here of expression contains more than one statement, should be executed when this is true. Okay, then you surround your case by a begin and end. Okay, so this is also the generic form of the if statement. Let me just drag this to the other side here so that you can see it. You can see that whenever you have more than one statement in your if statement in which this is true, you want to execute more than one statement, okay, for the if statement, then you surround it by a begin and end. Okay, otherwise the begin and end are optional. You can put them, but they are not required for a single statement. Okay, all right. So coming back to this, let's move on. So this is an example of a full adder implementation or modeling using an always block instead of what we call an assign statement. Okay, so here we have a register S. Remember, when your output is coming from an always block, it has to be a register type register. Okay, so it's an output and then reg S. Okay, and then also notice that this output reg also affects C out as well. Okay, so C out is output reg as well. And then we have input. These three are wires, just wires. Okay, A, B, and Cn. So always at any change in A, B, or Cn, you remember the full adder has three inputs, right? It's A, C, B, or Cn. Okay, whenever one of them changes, you need to re-evaluate S and C out. Okay, so we re-evaluate S and C out using this blocking assignment. You can see here that we're using blocking assignment to evaluate S and out. Why do we use blocking assignment? Because this is a combinational circuit. It's not a sequential circuit. Okay, just for now, just take this as a fact. Do not think about it. Whenever you have a combinational circuit, use a blocking assignment. Okay, so S will be computed first, and then C out will be computed next. Okay, it doesn't mean let's not talk about the clock cycle. Let's not talk about the clock. Okay, for now. Later, when we cover sequential circuits, you'll understand what is the difference between blocking and non-blocking assignment. But for now, just think about it like this is going to be executed first, and then this is going to be executed next. So if your C out is dependent on S, then this is going to work as well. Okay. So if you remember, one of the ways that we implemented the full adder was that C out is what is A XORed with B ended with Cn ORed with ORed with what is it called? It's this ORed with that. I mean, ANDed with this, or ORed with Cn. Yeah, Cn. No, A. Yeah, A ANDed with B. Yeah, A ANDed with B, isn't it? Yeah. So this is A ANDed with B. Yes, it's one of the OR inputs here. So this is nothing but this implementation here with the XOR expanded to be AND OR. Okay. Yeah, I believe so. Actually, one of the so if you want to get this expression exactly, then you need to derive the truth table of C out in terms of A, B, and Cn, and come up with a K map. Okay, the K map will give you exactly this expression. Okay, so I'll leave it for you to exercise. All right, but just make sure that you get this. That this is nothing but what we did so far. Okay. Okay. What about an implementation of a comparator using a sign statement now? Okay. Remember, sign statement is also behavioral. Okay. Before I move on to a comparator, remember that full adder is a single bit, so we don't need a parameter here. For the comparator, we have an input signal here, which has a width. Okay, a width as a parameter. B has the same width as well. Okay, so A and B, they have the same width. All right, which is defaulted to 32. All right, and then we have three output signals: either A greater than B, A less than B, or A equal B. All right, so we are using the Verilog relational operator to generate these signals here. All right. So first of all, A and B are wires of a width bit. So we have input width -1 to 0. All right. And then for each one of the output, it's just a single bit. Okay. Single bit wire. For A greater than B, it's assigned the value. Okay. It's a continuous assignment. Whenever A is greater than B, okay, this is true, then this is going to be true. If this is false, then this is going to be false. Similarly, for less than and equal to. So equal to, remember that equal to, in order to test for equality, you need a double equal sign. You need a double equal sign. Do not confuse this with the assignment here. Okay, assignment, okay, is a single equal sign, whereas the double equality here is for testing equality. Okay, so this expression here returns whether A is equal to B or not. So this will infer the implement or the synthesis of a comparator in the background. So all of these, okay, will imply that a comparator will synthesize this module here, comp. Okay. All right, moving on. So another way of implementing the comparator is using the always block. Okay, so again, if you're using the always block and the output of the comparator is A greater than B, A less than B, and A equal B. So these needs to be registers. Okay, you see that they are registers now. The output, and they are registers of size 1. Okay, they are 1 bit. Each one of them is 1 bit. Okay, this is only because they are in the always block. Inside, they are assigned in blocking assignment using the always block. If you go back to the previous implementation, we didn't put reg here, okay, because they are not inside an always block. They are part of a continuous assignment, okay, continuous assignment statements. So here we use reg because it is part of an always block, and we initialize all the signals to 0 first. This is very important. We initialize all the output signals to 0, and then, okay, we set the one of them to 1 according to this if statement here. So we test for equality first. If this is true, then equal is 1. Else if A is greater than B, then the greater will be 1. Else the less than will be 1. Notice that we don't have to write the if statement for the final one, because if A is not equal to B and A is not greater than B, then it must be less than B. Okay, so one at the end, one of these signals will be 1, and the rest of them will be zeros according to this initialization. Yeah, this initialization is very important. If you don't initialize, the code will be wrong. Okay, because it will take the previous value. Okay, and then you may have more than one output, which is 1. Okay, so this is wrong. In the comparator, only one output is 1 at a time. All right, I cannot stress this more than that. It's very important to initialize your output signal when they are inside an always block. Okay, unless of course they are generated using one statement, like the case in the full adder here. In the full adder, they are actually generated in one statement. Okay, and also there is no other signal that is affecting this. In the comparator case, okay, it's it has to be that one of them is 1 and the rest of them is zeros, and then the only way to do it is to do it this way, or you can do it the hard way. Hard way is to do it this way. Instead of this, okay, you can say, well, if A, for example, let's start with A equal to B, and you say begin, and then you say, well, A equal B is 1, and A less than B is 0, and A greater than B is 0. Okay, in this case you're fine to do that, and then you say end here, not yeah, and then else if, and then else if. Okay, and then you say, well, A is greater than B. Then begin, another begin, and end. Okay, in this begin you will copy this, right? But you change the one that has the 1. Okay, change the output that has a 1 instead of equal. Now it is what? It is greater than. Yeah, it is greater than. So here we have a 0 here and a 1 here. You get the idea. So you need one more else for the less than. Okay, so instead of having this long code, you use this short code here. Okay, and in order for this to be the same equivalent, you have to initialize the 3 signals to 0 and then check which one of them is going to be 1. Okay, this is an alternative way of doing it, but it's the bad alternative. Okay, this is the bad way of doing it. Alternative. Okay. All right, moving on. Now this is an arithmetic unit using an always block. Okay. This is another example. Okay, so here we have again we have the output, which is Y and C out. Both of them are declared as registers. Okay, because they are assigned inside of an always statement. So in the always statement, we execute the always statement in case A changes, B changes, or select changes. Okay, so when select, we have a case statement here. When select is 0, 0, we have C out comma Y concatenated together equal A plus B. All right, and when it is 0, 1, we have this again to be A minus B, and then 1, 0, A plus B, and then 1, 1 to be A minus B, and then we have the default. Okay, then we have a default value, a default case in which C out is going to be assigned to 0 and Y is going to be assigned to 0. And then you have a begin and end, because this is 2 statements here. Why did we use the default here? Why have we used the default although we have listed all the signals? The reason for that is to account for unmentioned values of select. Okay, so this is fine. Okay, this is fine if your output is among these. This is the default case. This is the normal case. Okay, is that your select is one of these. But if one of the bits of select is let's say in error, okay, it's high impedance, let's say it's not connected to any input, okay, then one of the errors will be incorrect, and the other bit will be correct. So in this case, the always block will go to the default case in which both the carry out and the Y will be 0. Okay, this is in case. And then you have, by the way, case, okay, is ended with end case, not end. Okay, and it doesn't have begin. So case, end case, just like module and module, a case has its own end statement, which is called end case. Okay, so for the module, you don't have begin, but you have end module, a specific instruction to end the module. And also for the case, you don't have a begin, but you have end case. Okay. This is also another example of a logic unit, okay, in which we have 8 functions now. Actually, we have 3 selection lines, okay, 3-bit selection line, which is 2 to 0 here, selection, but we are only using 6 functions here, okay, and for the remaining functions, we're outputting y equals 0, okay. So for each function here, this is AND, for example, this is OR, this is XOR, this is one's complement. You can see One's complement means the bitwise complement, yeah, bitwise inversion of A. Okay, and then this is A NAND B, and this is A NOR B. This is the correct way of writing A and B, NAND B. So A NAND B is written like this, not A and B. Okay, this is A NAND B. It's not like the some of you have written in the exam, in the midterm exam, some of you have written this, A, not and B. This is big X here. It's wrong. This is not NAND. This is basically, this will result in a syntax error because this operator here is a unary operator, I believe. It's a reduction operator. Okay, let me just go back to the operators and find out that. Okay, it's way back. Yeah, here. So this is reduction NAND. You see, it's reduction NAND. So what happens is that you are going to NAND all the bits of the variable, and in our case, it's this. Okay. Uh, this one, yeah. So you are going to, in this case here, okay, what you're saying that is that you are going to NAND all the bits of B and then do what with A? Okay, so you're saying A and then saying something like B or C. Let's call it C. Okay, C, where C is not and B. Okay, so this is going to cause a syntax error in Verilog because there is no operator in between the two. Okay, I just hope that you understand and get this. All right, next we have a 2-to-1 multiplexer. This is going to help you in the homework problem. Okay, so you can take this as is from the slide. Okay, when I ask you to develop a 2-to-1 multiplexer, this is where you get it from. Okay, so we have three methods using a sign statement. For example, here we have three inputs: A, select, B, C and B. Okay, and then A. Okay, so we can say, well, A is equal to select question mark. If the question mark is true, then it's B, otherwise it's C. You see, B or C. The next one is to use an always, using an if statement. Okay, so we have an always block at any change of C, B, or select. Okay, you can see here select B or C. Then we execute this if statement, which says if select equal A equal B. If select then A equal B. Otherwise, A equals C. Okay, it's just the if statement associated with the multiplexer. This is a behavioral description of the multiplexer. Okay, and then the final one is to implement this multiplexer using a case statement. Okay, case statement. All right, so you have here the case for select, and when select is 1, you pick B for A, and when select is 0, you pick C for A. And notice that these assignments are are combinational logic assignment or blocking assignments. Okay, and notice also for this one here, the output. Just use the pointer. The output A, okay, is not a register here. It's a wire because we are using the continuous assignment here. But here it is a register. It has to be a register, otherwise you'll get an error. When your output is coming from an always state and always block, then it has to be marked as a register. Okay, this is a rule in Verilog language. Okay. All right, moving on. So this is an encoder implementation of a Verilog module to implement an encoder. Remember the encoder, what does it do? Encoder, this is an 8 to 3 encoder, I believe. Yeah, an 8 to 3 encoder. So we have 8 inputs. 1, 2, 3, 5, 6, 7. Okay, and and view size. Yeah. Okay. Don't worry about this. Okay. So we have here inputs here, and actually my input is coming into a bit vector. Okay, the bit vector here is actually a bus that is feeding all these lines. Okay, this bus is of size 8-bit. Okay, and then the 8-bit are splitting between the bits of the input of the multiplexer of the decoder of the encoder. Okay, so this is an 8 to 3 encoder, and then your output is going to be 3-bit. So this is bit number 0 of the output, bit number 1 and bit number 2. Okay, and then we have a bus that combines all of them, and this bus is 3-bit. And the bus name is here, the output name is code. So this is code. And the input name is data. Okay, data. Let me write it here. You can see that data is what? 8-bit. Okay, and the code is 3-bit, and it is marked with a register keyword because it's assigned inside of an always block. So always at any change in data, which is the input, okay, then you have to execute this if else statements. Okay, so if my data is 1 and my code is 0, this is how the encoder works. Okay, it tells you exactly where is the bit that is on. Okay, so this is 0, it means that bit number 0 was on. If it is 1, then bit number 1 was on. So here we have else if, okay, data equals this, which is 2 here. Okay, then my code will be 1. Okay, else if, again, if it is 4, okay, 100, then it's 2 because bit number 2 is on. This is bit number 0, 1, 2. Okay, let me go here, for example, else if it is this number, then my code is 6. Okay, because why? 1, 2, 0, 1, 2, 3, 4, 5, 6. Bit number 6 is on, and so on and so forth. And this is the final value, the final valid value. This is, remember, this is just an encoder. It's not a priority encoder. So one of the bad things about encoder is that when it gets the wrong what we call input, it will not produce valid output. So we don't care about the output when the input is invalid. So the only valid inputs are these 8 patterns. Whenever the input is anything else, so this else statement covers, then my code is I don't care. Okay, my code is I don't care. So this is an encoder. Let's see. Yeah, and here this is a priority encoder. Okay, the priority encoder has 2 outputs basically. Here we are using both always and continuous assignment. We're using a continuous assignment for the valid output, okay, which is basically the reduction or of your data bits. If this is 1, then you have a valid data. If this is 0, then you have an invalid data. Okay, if you OR all the bits of data, okay, and you find out that the result is 0, then it means that your input is 0. But if you OR them and you get the result as 1, okay, then your input is valid and you can prioritize the bits according to this always block. Okay, so now this is we are giving the most significant bit here the highest priority. So we check it first. We check if data 7 is 1, then the code will be 7. Else, what does else mean? It means that data 7 is 0, it's not 1. Okay, then we check 6. If the 6 is 1, then my code would be equal to 6. Okay, else means that my data 6 and data 7 are zeros. Okay, so we check the next one, which is 5. Then my code will be 5 if this is 1. Okay, and so on and so forth. But In the final part here, you can see that the final else here, it means that my data is not valid. Okay, so all my bits are zeros, so my data is not valid, so I don't care about my code output. So my code output will be, I don't care here. Okay, so this is a priority encoder. All right, what about using the K6 statement? Instead of using the case statement, we can use the case X statement. And using the case X statement is really more intuitive when compared to the what we call the truth table of the priority encoder. It basically lists the truth table. Okay, so here we are listing the values with the X's here, with the don't cares. So you can see the case data. Okay, we have a 1 here, and then don't cares for the rest. We have a 1 here, and then we don't care about the rest. So the output will be 7. This is the next case here. The next case, we have a 0 here and a 1 here, and then the rest are don't care. So this is going to be 6. And so on and so forth, okay, until we reach the end here in which the data is not valid, so we don't care about my code. Okay, so when can you use the don't cares in your select statement? Only when you use case X statement. Okay, and again, valid data is assigned outside the always block using the continuous assignment. Notice, again, I repeat this, it's important that code, okay, since it is assigned inside the always block, it is marked with a register keyword, okay? Whereas valid data is not, even though it's another output, is not marked as a register because it is assigned using a continuous assignment statement, which is outside the always block. You cannot place the continuous assignment statements inside the always block. This is not possible, okay? It has to be either, the signal has to be computed using a continuous assignment statement or using an always block. Okay. This is an implementation of a decoder, okay, which is the inverse of an encoder, okay? So it's straightforward. Again, you have an output range here because it's the value here of data is assigned inside the always block. And we check for every input pattern, okay, which one is going to be on, okay? That's straightforward, okay? If my code is other than these, okay, for example, contains a high impedance or something like that, then my data is going to be I don't care. Okay. Next, we are going to implement. This is the final slide. Okay, we are going to implement a 7-segment display decoder. 7-segment display decoder using Verilog. Okay, this module here is called 7-segment display. Okay, and it is using Verilog to implement it. Okay, so this module here has one output, which is called display. Okay, that will supply the 7-segment display unit with the legs that are on. Okay, the legs that are actually the legs that are. Let me see. If this is 0. Oh, okay. No, the legs that are, yeah, the legs that are on, okay, but it is inverted, okay, it is inverted. So when a signal is marked with, when a segment is supplied with a 0, it is on, and when it is supplied with a 1, it is off. So essentially, this is an AND decoder rather than I mean, yeah, rather than a simple AND decoder, okay? So here, when it is blank, okay, we are defining some parameters, constants, okay? This blank here is this 7 segments here. All the segments are off. Okay, you can see that. All the segments are off here, all right? And then for 0, okay, we have all the segments off except, all the segments on except one that is off. Okay, now for the 0, you know that this is for the 0 here. Okay, all of these segments are on and this is off. So you know that this bit here is for G. Okay, so the order is A, B, C, D, E, F, G, just like what is written here. Okay, and 1 is B and C. You can see 1 is B and C, and the rest of them are ones. Yeah? We have 1, 0, 0, and then 1, 1, 1, 1. Remember that the underscore is only for readability, and it will be ignored by the compiler. So this one here, this number here, corresponds to the binary number 1, 0, 0, 1, 1, 1, 1. Okay, this is by the eyes of the compiler. It will ignore the underscore. And then you can also verify that each number, each actually digit corresponds to its segments here. Okay, for example, let's take 7, for example. 7 says that A, B, and C are on and the rest are off. So this is A, B, and C. This corresponds actually to 7. Okay, so it's just a matter of assigning which segment to display and which segment to turn on and which segment to turn off. Okay, so we have an input called BCD here, all right, and an output called display. So we have a case statement here on BCD. When BCD is 0, my display, okay, is going to be assigned the value 0, which is what? Which is this. It's just a constant here, okay, just for readability, all right? And then when it is 1, my display is going to be assigned the value 1, and so on and so forth, okay? Up to 9, okay? When it is 9, then the display will be 9. Otherwise, okay, the default case, okay, is going to display a blank, all right? Blank means none of the segments are on. Okay, and no segment is on. All right. This concludes my lecture about Verilog. Okay. Most likely, I will probably include another short demonstration about the behavioral modeling. Okay, that will help you through the homework. Okay, through the homework. But I'm not sure when. Anyway, I'll let you know when I do it. Thank you. Let me stop recording.